I welcome you all in this course on refrigeration and air conditioning. Today we will discuss on air distribution system. In a building, not only, I told you earlier and repeating again, not only temperature and inside temperature or humidity, relative humidity are important, but also the quality of air is important. Air distribution is equally important. Air distribution is equally important. You may have cold air, but how to distribute this cold air into the entire building? For small capacity systems like direct expansion, package type of unit, you can, there are different type of air conditioning unit. One is we normally use this split AC or window type of AC. But if the cooling load in a building is, let us say, 5 kilowatt. So, for 5 kilowatt it is not recommended, or 6 kilowatt it is not recommended that you go for multiple units of window type AC. Instead of that, a package type of system is recommended. A package type of system, package type of air conditioning system is a unit you can keep at the rooftop, and air will be circulated in the entire house through the ducting. Though it is not in fashion, but as far as the energy conservation point of view, such type of arrangement should be made, and ducting should be done in the house. Nowadays very beautiful designer ducts are available in the market. So, ducting can be done and air can be distributed in the different segment of house or a small building or a restaurant. Now, if the cooling load is more, then we go for centralized air conditioning system. In the centralized air conditioning system, in the basement of the building, a room is there where compressor is located, and this compressor, in fact, in the vicinity of the compressor there is a evaporator also. In fact, it is not an evaporator, it is a chiller. So, in the chiller, cooling water is chilled. That is for the high capacity. Suppose the capacity is 100 tons or 200 tons. In that case, chilled water type of system is used. So, we can go for a package unit. If the capacity is high, we can go for a centralized cooling system where air will be centrally cooled in the building. Suppose the cold load is 30 tons. So, air will be centrally cooled and air will be circulated in the building. This is known as direct expansion type of system. Now, if the load is high, suppose 250 tons, now we want to have 250 tons of refrigeration, and I told you the thumb rule that 400 CFM per ton. So, if I take 400 CFM per ton, 400 CFM per ton, so it is going to be 1 lakh CFM. 1 lakh CFM is approximately 50,000 liters per second. I am just telling you how much bulk of air has to be handled by the system. Now, if this bulk of the air which is to be handled by the system has to be for the movement of air, we need blowers and big size blowers. They are known as AHUs, air handling units. Air handling units are, they consume a lot of energy. Suppose there is a multi-storied building. So, normally on each floor or between or after alternate floor, the air handling units are placed. They are blowers. They circulate, air handling units are used for circulating air in the building. Suppose the cooling capacity of air conditioning system is 250 tons of refrigeration. In that case, we will be using around 250 into 400, 400 into 250, around 1 lakh, 10 to power 5, 1 lakh CFM shall be required. It is going to be approximately equal to 47,000 liters per second. In order to handle this type of fluid, huge AHUs will be required. Instead of doing that, chilled water is used. Chilled water is here as secondary refrigerant. Now, chilled water takes heat from the building and this heat is subsequently transferred to the refrigerant in the centralized cooling system. However, if the capacity is low, for example 50 tons or 60 tons, we can go for direct expansion type of system. In direct expansion type of system, the air is cooled in the centralized cool and it is circulated in the building. For the circulation of air handling units are required. Air handling units are nothing but fans and blowers which make circulation of air into the building. Mere circulation is not sufficient. Air diffusion is also important in the building. So, we will take up first the air distribution in the building through the network of the ducts. So, for the distribution of air in the building, air handling units are required, and for air handling units we need to have size of the duct, because if we take larger diameter duct, the air velocity will be very less, okay, and it will attract more cost. If we take smaller size of the duct, air velocity will be very high, at the same time pressure drop will be very high. Suppose single duct, now we are bifurcating the duct. There will be a pressure loss. The pressure losses in the bands and such type of splits we will discuss in subsequent lectures, but definitely conservation equation here it will hold good. Suppose cross section of this main duct is 1 meter square and the split is 0.75 meter square and this is 0.25 meter square, then velocity is, let us say, 15 meters per second. So, discharge here 15 into 1, total discharge A1 V1, or then suppose velocity is equal to 0.75 velocity here plus 0.25 velocity 2 V2, this is V2, right. So, I mean the all conservation of law of fluid mechanics are applicable here in the case of duct design, and definitely if it is M1, M2 and M3, then M1 is equal to M2 plus M3. These processes are adiabatic processes, so there is no heat loss. We can also use M1 H1 is equal to M2 H2 plus, but that will not be very useful here because we do not consider here normally in the distribution of air the heat transfer as well. If you want to, if it is required, it will be considered. If it is required, it will be considered. So, these are the preliminaries in duct design. Now, room air distribution, when the air enters the room, occupied zone is normally considered 6 feet above the ground level. Now, our focus remains, or focus of study normally remains upon 1 meter, 1.8 meter above the ground level. And last 2 points I have already stated that in the maximum variation inside a room should not be 1 degree centigrade. So, air should be distributed in a room in such a manner that the temperature differential in a room is not more than 1 degree centigrade, and temperature differential within a room, within different rooms should not be more than 2 degree centigrade. Draft I have already explained to you, that is a localized feeling of warmth and coldness due to movement of due to both air and temperature and air movement, while humidity remains constant. So, draft I have already covered in the previous lecture. Drop is the vertical distance traveled by traveled by the air stream. Suppose air stream in a building is entering from this side. So, vertical distance covered by the air stream is known as drop for reaching to opposite wall. So, that is drop. Now, for designing a duct, commercial, industrial and residential air duct system design must consider the following points: available space, space air diffusion, how much space is available for air distribution, that is important. Space air diffusion, noise level, what is the noise level? Because noise level, if we reduce the diameter of the duct, because cost has to be taken cost also has to be taken into account. If you reduce the diameter of the duct, the cost will reduce, but at the same time velocity will increase, that will subsequently lead to the friction pressure drop inside the duct. So that is and on the other hand, if we maintain lower velocity, that is also not recommended, that very low velocity is maintained inside the duct. In that case, size of the duct will increase, and for low velocity ducts, other problems like stale air problem shall also be come into the picture. So duct noise level, but duct noise level, I mean, it is a criteria while designing a duct. Duct leakage from duct takes place because the ducts are riveted, and whatever state of the art technology used, some leakage will be there from the duct. It has to be confined to less than 10% of the total air discharge in the system. Duct heat gain and losses, so ducts have to be insulated, because air which is moving the duct, as you have seen in the load calculation, it is of the order of 13 degrees centigrade or 14 or 15 degrees centigrade. If outside air is humid, the condensation over duct surface will take place. So duct surface will come in contact with the outside humid air. Suppose outside air is 35 degrees centigrade temperature and 70% relative humidity or 80% relative humidity. The moment this air comes into this contact with the duct, because the dew point temperature for this air may be, let us say, 17 degrees centigrade. I do not know the exact value, but maybe if the dew point temperature of outside air is more than the surface area of the surface temperature of the duct, condensation take place, and this phenomena is known as sweating of the duct, and this must be avoided. You must have seen in some of the buildings discolored walls in the vicinity of the duct. That is due to sweating of the duct. The ducts were not properly insulated. That is why when the humid air came into the contact, hot and humid air came into the contact with the duct, subsequently the condensation took place, and air, the water which was formed, water vapor which was condensed on the duct surface, subsequently it discolored the wall. So if you must have observed such type of things in many of the buildings. Now balancing is important. Suppose air is supplied, there are number of openings, and each opening certain amount of air has to be supplied. If proper balancing is not done, in this case, in this farther area, farther openings, we may get less air, and the openings which are closer to the fan or AHU, excess of air is supplied. This is known as poor designing of air distribution system. If we are not getting the required amount of air at the openings, that is known as imbalance in the system design. Fire and smoke control is a must, because if there is a fire propagation in the building, the smoke propagates very fast through the ducts. Initial investment cost, I have told you the criteria for initial investment cost and system operating cost. So AHUs and all are to be used. So that is the system operating cost. Now duct noise level can be measured with the help of this. This is decibel power is 10 plus 50. This is a very simple formula, log of velocity plus 10 log of area. Suppose a duct is having a diameter of half meter, 500 mm duct, 500 mm diameter circular duct. So area is going to be pi by 4 into 0.25 square, and that is going to be equal to 0.049 meter square. Now area and then velocity, duct velocity, let us say 20 meters per second. So noise level we can calculate as 10 plus 50 into velocity is 20 plus 50 into log of velocity, that is 20, plus 10 into log of area, that is 0.049, that is 61.95. Approximately, this is a log scale. We can, okay, let us take 62 decibel. The 62 decibel noise is the noise which somebody talks. It's normal conversation. So this is the voice of sound level of normal conversation. So this much of sound shall be created, because sound, if sound level in a duct is high, in that case you may feel comfortable thermodynamically. Thermally you may be feeling comfortable, but otherwise you will not be comfortable in that occupancy where noise level is very high. So noise is one of the criteria for designing the size of the duct, because if we increase the velocity, noise level will increase. If we say here the area, because velocity is remaining constant. Okay, so area cannot be justified here, but if we are increasing the velocity for the same area, the noise level will increase. And if we increase area for the same velocity, it means more air is flowing. In that case also the noise level will increase. So pressure drop in a duct can be contributed to two factors. One is duct friction, another is change in direction or velocity. So duct friction is delta P by L is equal to half F rho V square by D. This is duct diameter, and this is the pressure drop per unit length. And change in direction and velocity, definitely when there is a change in inertia, pressure drop has to be there. So if there is a change in the direction of the fluid, pressure drop will be there, or if there is a change in velocity, I mean if there is an increase in velocity, there is going to be a pressure drop. Now this is a duct friction chart. Before I start duct friction chart, I will tell you, because all the ducts are not circular. Some of the ducts are rectangular, right? Now in those rectangular ducts, what we are going to do? For those rectangular ducts, if I want to take this chart, because this chart is only for circular ducts, suppose this is A and this is B. So for a rectangular duct, the equivalent diameter is going to be 1.3 A plus B raised to power 0.625 divided by, sorry, it is reverse, AB raised to power 0.625 divided by A plus B raised to power 0.25. So this is the diameter of, equivalent diameter of the duct, which has a rectangular duct which has sides A and B. A and B can be either of the side. So for this AB side rectangular duct, this is going to be the equivalent diameter. Some of the ducts are oval shape, right? In oval shaped duct, suppose this is a major axis and this is minor axis. Then area of this is going to be pi A square by 4 plus A minus A, and P is equal to pi A plus 2 A minus A, and equivalent diameter in this case is going to be 1.55 AR raised to power 6.25 divided by P raised to power 0.25. So in both the cases, whether it is a rectangular duct or a oval shaped duct we have used these formulas. We have taken area and this perimeter, function of perimeter, function of area. Here also function of area and function of perimeter, and we will get the equivalent diameter. So, we can get equivalent diameter for both the ducts, whether it is a rectangular or a square duct or an oval shaped duct. Now, we will see a friction chart for a round duct. This is a friction chart for a round duct. On the x-axis, on a log scale, the air quantity is shown, starting from 20 liters per second to 2 lakh liter per second. It is on a log scale. On a vertical axis or y-axis or ordinate, friction losses in Pascal per meter. Friction losses in Pascal, delta P by L, Pascal per meter is given, and these friction losses starting from 0.1 Pascal meter to 100 Pascal meter. 100 Pascal meter is very high friction loss. Similarly, 2 lakh liters per second are also very high discharge rate. So, however, the vertical lines here, it means vertical lines in this chart, are for air quantity, constant air quantity. Horizontal lines are the pressure, constant pressure drop. This chart is for friction chart for round ducts. The density of air is assumed to be 1.2 kg per meter cube, and roughness of duct surface, GI duct surface is 0.09 millimeter. This chart is taken from Ashray Book of Fundamentals for 2013. Now, it has inclined lines, these inclined lines. These inclined lines are constant duct diameter line. So, this line is a constant duct diameter line. Now, perpendicular to these lines, again we have dark lines. These lines are constant velocity lines. Now, with the help of this chart, the dimensions of duct can be easily calculated. Suppose I will take one example. Suppose friction loss in my duct is 1 Pascal per meter. So, friction loss is per 1 Pascal meter and discharge is 2000 liters per second, or friction loss is, let us say, 2 Pascal per meter and discharge is 2000 liters per second. So, in this case, the duct diameter is going to be 500 millimeters. This is equivalent duct diameter. If I want to have a rectangular duct, I will have to use the equation for rectangular duct, that is AB, and that equivalent diameter is equal to 1.3 AB raised to power 6 to 0.5 divided by AB raised to power 0.25. And then if normally ratio or AB, let us say if the A and B ratio is 4, that is A by B is 4, then using these two equations we can find the value of respective value of A and B for rectangular duct. Same exercise can be done for the oval shaped duct. Now, here at this discharge, this pressure, the duct diameter is 500. If I increase the diameter of the duct for the same discharge is same. If I increase the diameter of the duct from 500 to 830, right? In that case, the friction pressure drop will reduce to 0.6 simply by increasing the size of the duct. If I further increase the size of the duct to 800, sorry, this is 630, not 830, this is 630. So, 500 to 630, 600 to 800. So, if I further increase size to 800, the pressure drop per unit length will be reduced to 0.2. So, starting from 500 millimeter duct, for friction drop 2 pascals per meter, if I take 800 mm duct, the friction drop will be reduced to only 0.2 pascals per meter. So, in the network of ducts, there are going to be ducts of different length and different discharge. For that network of ducts, we can find the diameter of individual duct using this chart. In addition to that, using this chart, we can find the total pressure drop in the system, which will help us in deciding the size of air handling unit. Rest of the things regarding the air distribution system will be covering in the next lecture. That is all for today. Thank you very much.